Just a little more about resonance structures then. The resonance structures that we saw with the formate ion, actually both of them would be what I call major contributors. They both totally make sense. Sometimes one is a little more favored than the other with regard to energy stability, and sometimes it's kind of a non-starter. The one resonance structure does not make sense. We're going to look at an example of that here in a minute. So, like you said, like you saw a minute ago with the formate ion, actually, what really happens is what we call a hybrid of the two. Okay, where electrons are delocalized. So, how do you know whether a resonance structure makes sense? And actually, this is an aspect of that's going to enter into you drawing your own Lewis structures. You're going to have a possibility at when you draw a Lewis structure, your last step is to pull in electrons, lone pair electrons, and make them into a pi bond if your central atom needs more electrons. And you're going to have to try to figure out which atom do you pull them from. So let's see, which one? Well, I'll try to kind of show you. I'm trying to see. You're gonna pull it from the atom that gives the expected valence. Expected valence, okay, is satisfied as you pull electrons in. Actually, I'm going to show an example here in a minute of what I mean by that. Remember, expected valence is what? 8 minus the group number. And expected valence is the number of sigma and pi bonds an atom is associated with. Okay, so yeah, I guess this is the one that I just said a minute ago. Now, we expect that an atom will follow its 8 minus the group number. That's the number of sigma and pi bonds it's going to connect up with, only though if that atom is in a neutral molecule. So we're actually going to be drawing the Lewis structures of some polyatomic ions, like formate is a polyatomic ion, and in that case they don't follow this rule. Sorry. So the example I want to take a quick look at is carbon dioxide. Let's come up with the pot of valence electrons right quick so we make sure both of these structures are legit. Carbon, okay, there's one carbon atom. It's a 4A element, though, so there are 4 valence electrons. Oxygen, there are 2 oxygen atoms. Oxygen is 6A, so they both bring 6 valence electrons. Okay, so we're looking at 16 valence electrons to distribute around those 3 atoms. Carbon has the lower electronegativity. We're going to put it in the middle and both carbons on either side. So notice that both of these structures, what they do is make sure we have 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. I'm liking it. 2, 4, 6, 8, 10, 12, 14, 16. So they both have 16 electrons. Then let's go ahead and check to make sure each atom has a complete octet. I'm liking 8 electrons there, 8 electrons there, 8 electrons there. What do you think over here? This one looks lopsided, doesn't it? Looks lopsided. 8 electrons. They've still got complete octets for each of those 3 atoms. Now, one of the things, and like I said, you're going to run into this on homework and maybe on a test, but the expected valence. Okay, valence. Oops. Valence is 8 minus the group number. So what is the expected valence, and we talked about this before, of carbon? Well, carbon's 4A, so 8 minus 4 is 4. So we expect it to reach out 4 times. Is carbon reaching out? Now these would be sigma and pi bonds. We got it reaching out 4 times here. Yep. Sigma pi, sigma pi. How about over here? Yep. Sigma, sigma, pi, pi. 4. What is the expected valence of oxygen? Well, oxygen is a 6A, so 8 minus 6 is 2. So we expect it to form 2 total sigma and pi bonds. Starting over here on the left, Is this oxygen reaching out 2 times sigma pi bonds? Yep. This one? Yep. Okay. What about this oxygen right here? Is it reaching out twice? No. It's just reaching out once. So it actually, what we say, violates its expected number of sigma and pi bonds that oxygen is reaching out. Now again, this only happens in neutral molecules. This rule of expected valence, is this a neutral molecule? Yes. So to me, this right over here says that this is a non-contributing resonance structure of carbon dioxide. All right? Okay. So here is your assignment.